Hi everybody, hope you're having a wonderful day. Today we're going to start chapter 14, which is about gases. We're actually skipping chapter 13. We will do 14 gases first, and then we'll go back to chapter 13, which talks about solids and liquids and states of matter in general. So we are going to start the chapter with a brief overview of solids, liquids, and gases, the position and the motion of the particles. So as you can see, solids, they are tightly packed, very close to each other, condensed together, and they are in these nice repeating units called crystals. So they're very, very ordered. In terms of liquids, they are pretty close to each other, again, very condensed. The spacing between those particles is almost the same as the spacing in solids. The big difference is they are very random. You don't have that nice repeating unit or nice structure in the crystal. Gases, as you can see, they're very far apart from each other, and they're very random. In terms of motion, solids are stuck in their place in that crystal, in these rows and columns, and they're vibrating in place. Liquids are able to slide around each other, and then gases are just going crazy. They are going very, very fast and very randomly. In terms of energy, in physical science, and probably in 8th grade as well, you've learned about two main types of energy, potential energy and kinetic energy. So let's start with potential energy. Potential energy has to do with position of the particles. And you probably remember when you used to calculate potential energy, it has to do with like the distance from Earth, and you'd say P is equal to PE is equal to mgh. You do not need to know this equation. This is just to kind of like refresh your memory of what potential energy is. So potential energy, if you wanted to calculate it, you would look at the mass times the gravity, the pull, times the height. And so if you are flat on the ground, you had zero potential energy because you are really close to the Earth, which is attracting you. The higher you go, so if you climb on a mountain or on a ladder or something like that, the farther you are from what's attracting you, which is the gravity of Earth, the more potential energy that you have. That means the more energy you need to keep you away from that attraction, the farther you are. So here it's the same idea. It has to do with position or distance, but in this case it's not gravity that's pulling. In this case it is the attraction between the particles that is pulling. And so any two particles have masses, and so they attract each other. And so the closer they are, the lower the potential energy. The farther away from each other they are, the higher the potential energy. And so in terms of this three states of matter, we can see that solids are the closest to each other, so they have the lowest potential energy, followed by liquids. And then gases are drastically higher in potential energy because the particles are so far apart. So it takes a lot of energy to keep them in that position. The other type of energy that you've learned about is kinetic energy. And if you remember, it is equal to half mv squared. Again, you don't need to know that equation. This is just to talk about it, to remind you of what it means. So it has to do with speed. V is velocity or speed. And kinetic energy is related to temperature. So if I'm measuring the temperature, I'm basically measuring the average kinetic energy. And so the faster the particles are moving, the higher that kinetic energy is, and the higher the temperature. So out of the three states, which one has the highest kinetic energy? Well, it depends on the temperature, right? Because kinetic energy is related to temperature. So if I have solid ice at 0 Celsius and liquid water at 0 Celsius, they're both going to have the same kinetic energy because they're both at the same temperature. But in general, solids tend to exist at lower temperatures, and so they tend to have low kinetic energy, followed by liquids. And then gases tend to happen or occur or exist at high temperatures, and so they typically have higher kinetic energy and they're moving faster. So again, it depends on what the temperature is. Sometimes your two phases might be the same kinetic energy, but in general, solids have the lowest kinetic energy and gases have the highest kinetic energy. So in both cases, for potential and for kinetic, gases would have the highest energy. Okay, next we're going to talk about kinetic-molecular theory, or KMT for short, which is a theory that has been developed to describe the behavior of gases, and it all has to do with the kinetic, the motion of the molecules. So kinetic-molecular theory has 6 different statements. You need to know all 6 statements, you could be asked on the test to tell me what the 6 statements are. So the first statement says that gases consist of very small particles, each of which have mass. So we know that gas particles have mass. If I were to take, let's say, a test tube with some solid iodine and it has a stopper, and so this is I2 solid, and I heat it up and I turn it into gaseous iodine, the mass should be the same, right? Because it's closed, no particles left, no particles came in, and so the mass of the particles should remain the same because I did not change my particles. I just changed the spacing between my particles. So particles, even in the gas phase, definitely have mass. So if you take in the picture here, we see an inflated balloon and a deflated balloon. So the inflated balloon would have a higher mass because it has the extra gas particles in there. Second statement says that the distance between gas particles are relatively large, and so volume of individual molecules is negligible compared to the volume of the container. So we're saying each gas particle between it and the next gas particle are huge spaces. This picture that we see here is not really correct. If the gas particles were that size, then the next gas particle would be like off the screen. There are huge spaces between them. And that's why gases are compressible. You can decrease that space and they fill up the volume of the container. Because of that, we can make an assumption that the volume of the actual gas particles are negligible, are not significant compared to the volume of the container, because the volume of the container is so huge compared to the size of the individual gas particles. So that's an assumption. Most of the time we can make it, but it is an assumption. Of course, gas particles do have volume, but we're just saying they're so small compared to the spaces between them, and so we're just going to say if I have a gas in a flask, I'm just going to take the volume of that flask, and that's going to be the volume that my gas is occupying. The third statement says gas particles are in rapid, constant, and random motion. They're moving all the time, they're moving randomly, and they're moving very fast. Next statement says collisions between gas particles are perfectly elastic. I don't know if you've studied elastic and inelastic collisions in physical science, but basically if you had a basketball, let's say, and you were to drop it on the floor, so it hits the floor, bounces back. It doesn't bounce to the original height like we see on the diagram on the left here. So it rises up, but not to the original height, and then falls back down, rises up a little bit lower, and so on. That's a normal collision. That is an inelastic collision. All collisions are inelastic, meaning that you lose some energy when things collide together. And the reason for that is if your basketball hits the floor, you lose some energy in terms of sound, you lose some energy in terms of heat, all kinds of friction, and so you get less and less and less energy. With elastic collisions, which is what we're assuming here, your gas particles collide, but then they bounce back with the same amount of energy. So it's like you drop a basketball, it hits the ground, and then bounces right back up to the same height. That doesn't really happen. It's not true, but it's an assumption that we can make because the amount of energy that they lose is really negligible. Next statement says that the average kinetic energy of gas particles depends only on the temperature of the gas. And remember we had said that the kinetic energy has to do with the speed. It also has to do with the temperature. So here we have the y-axis, the number of particles or the percent of the particles. On the x-axis, this is the speed of the particles, which is related to the kinetic energy or the temperature. So you can see here that there is a range of different speeds. So if I have a flask that has a gas in it, and I measure the temperature, not all the gas particles are moving at the same speed. Some are moving super fast, some are moving really, really slow, some are kind of in the middle. And so when I'm measuring the temperature, I'm measuring the average of all the different speeds. Now, what if I were to increase my temperature? What would this distribution look like? So it would shift to the right a little bit. So still, you have some particles that are moving really, really slow, some particles that are moving really, really fast, some are kind of in between, but the average, if you look at the red, which is at a higher temperature, is higher than the average of the black. So at a higher temperature, particles would be moving faster on average, but again, there's a wide range of speeds within your container. The last statement in KMT says that gas particles exert no forces on each other. What that means is that force of attraction or repulsion. In chemistry, when we use the word force, we mean attraction or repulsion. So in this case, we're talking about intermolecular forces. So we're saying there are no attractions between gas particles. Now, we know that's not true. That's an assumption because, of course, they have intermolecular forces. But because the gas particles are so far apart, that attraction is negligible, it's not significant. If you have two magnets and you get them close to each other, they're going to really attract. But if you hold them far apart from each other, they're not really going to attract very much. And so it's the same idea here. Gas particles do have intermolecular forces, but they are insignificant, they're negligible, because gas particles are so far apart from each other that that attraction doesn't really cause anything. So you need to know the 6 statements in kinetic-molecular theory, and you also need to know which ones are assumptions. So 2 main assumptions in kinetic-molecular theory. The second statement mentioned that gas particles have no volume. Their volume is negligible compared to the volume of the container. And that's an assumption that we can make most of the time, unless, like, you know, the container is really small or something. But it is an assumption. Of course, gas particles have a volume. And then the second assumption has to do with the elastic collisions and those no forces on each other. Those 2 statements have to do with intermolecular forces. So kinetic-molecular theory, KMT, says gas particles have no intermolecular forces. Of course, that's an assumption they do, but they're so far apart that their attractions are negligible. So KMT says gas particles themselves have no volume and no intermolecular forces.